Welcome back to Lecture 1 of Digital Integrated Circuits, and now we're going to the third part, which is called How a Chip is Born. So, I like this little caricature over here, how a geek is born. Okay, what does he say? He says, hello world. So how is a chip born? Well, I have a little flow chart over here on the right. We start with A&A and specification. A&A is architecture and algorithm. The output, basically, of this stage is a chip spec. Okay, how much memory, bandwidth, etc. do we need? Algorithms that include MATLAB C simulations that need to be implemented in hardware description language. Okay, once we have this specification, we can go to logic design and IP integration. IP is intellectual property. That's all kinds of blocks that were developed maybe by a different team or a different company that we bought. Okay, and we also do the logic design, which is where we take the detailed microarchitecture. The architecture, we make detailed microarchitecture. We say how we're exactly going to design our blocks, and then we write our design in a hardware description language such as Verilog. Logic verification is the next step. We take this design, this RTL, register transfer level design, RTL. What we usually call it, and we build a verification environment that will check if we have any bugs in there. So usually a verification engineer, he takes the spec, writes in a higher level language such as C++ or System C or E or one of these other types of verification environments, and tries to implement the spec. And then using the spec, they check the RTL, which was written by a different person, and see if we can find any bugs and how to fix them and so forth. Okay, once we finish with our logic verification and our logic design, we can go over to physical design, which is we're actually going to synthesize the design, make a floor plan, and implement it in test chip. We'll discuss that in a minute. Finally, we have sign-off and tape-out. Sign-off is where we go through all of the checks that make sure that everything was done according to the methodology of the company. We sign each and everything that it was done, and once sign-off is finished, we know that our chip should work, so we can go and send our files to the fabrication plant and the millions of dollars of costs that go with it, which is called to tape out the design. So let's go over this physical design flow slightly, just shortly. So we start with the standard cells, which is this library of gates, of digital gates, the inverters, the NAND gates, and so forth that fit in each of those rows, as I discussed before, and they fit some sort of standard. And we also go with hard IPs, which are blocks that we bought from a different company, a vendor, or we got from one of the other teams in our company. Memories, for example, are hard IPs. They're this actual layout and all the other files that we need. And in the course DVD, Digital VLSI Design, I discussed this in detail. Okay. On the other side, we have our RTL, our hardware description language code that we wrote. So these are the things we start with. We take the two of them and we input them into a tool called a synthesizer. The synthesizer is basically the compiler for hardware. Okay, what it does is it takes our code and turns it into generic gates. Then it maps these generic gates to the standard cells that we got, and also inserts the the hard IPs, and it outputs a net list, which is a list of all the gates that are actually going to be used and the connectivity between them. At the next stage, we design a floor plan similar to what we would do when we're building a house or something like that. But here we're building a chip, so we decide where the different parts of the things will go on the chip, including the different connections to the outside world, the IOs or the hard IPs, which are much bigger than cells, and where our core region is going to be, where we can scatter our standard cells. We put the net list that comes out of the synthesizer. This is a net list. Okay, we take the net list that comes out of the synthesizer, and we take the floor plan, we put it into a place and route tool, and it scatters all the standard cells around and makes connectivity and routes the things. Finally, when we finish that, or actually we do it several times in the middle, we do what's called static timing analysis that shows that we actually meet our timing constraints of our design, which we'll be discussing later on in this course. Okay, we take everything that came out and we have to run all kinds of physical validation checks such as DRC, LVS, logic equivalence, gate level simulation. I'll be discussing DRC and LVS in a moment a bit more. And once we've done this, we have signed off our chip basically, and we can send our files to the fab for tape out. when we go down into the circuit design flow, the custom design flow, which is what this course is basically focusing on, we start with a schematic. We draw a schematic, how the transistors, how the devices connect to each other. We take this schematic and we bring it into a simulation tool, and we simulate and see that we write a test bench, we simulate and we see that our circuit that we designed does what it should. If not, and it probably won't work at the first time, we iterate back into the schematic, we make changes and run simulation again and keep going around and around. Once we have our simulations working correctly, we go over to layout. We have to make a physical representation for the circuit that we designed. However, this layout will provide extra parasitics. So we have to run DRC and LVS, which are making sure that what we did in the layout is legal. That's DRC, design rule check, and LVS is that it's actually what we did. That's layout versus schematic. It tests that the layout in the schematic that we drew are the same. And then we run some extraction. We can call it RCX, which extracts the parasitics, the capacitors and the resistors and even the inductors that came out of our design that we didn't expect at first, or we didn't know about them at first. And then we can take this into a new net list that has these parasitics inside and run a post layout simulation. Of course, we may find differences here, and then we either go back to fix the layout to change the parasitics, or we see that we have to go all the way back to the schematic to fix the actual design itself. So let's discuss the CAD or the EDA tools that we use in this transistor level design, basically in the slide we saw before. Okay, so we have three basic tools that we're going to use: a schematic editor, a simulation environment, and a layout editor. Okay, so on the left side here, we have what our inputs are to this thing, what we get from the foundry, pretty much. Okay, so this is provided by the foundry. Again, that fabrication plant that it provides the technology and knows what it can make. So the first thing that it starts with over here is what we call a PDK, a process design kit, and that contains a whole bunch of stuff that we need in order to do transistor design. The first thing that's inside is a device library. So if we have an NMOS and a PMOS, and we may have different types of other things, maybe this type of a resistor or that type of capacitor and so forth that the foundry can make, they'll be part of the process design kit over here on the left side. On the other side, what we have is what the CAD provider gives us. For example, in Cadence Virtuoso, we will have something called the analog lib, which is different things like just a power supply or a type of a resistor, or just a generic resistor that works according to Ohm's law, and so forth. So on. That's going to be inside the analog lib. We have another tool which is called the hierarchy editor, which allows us to choose which view of the schematic we're going to actually simulate, if it's going to be the pre-layout schematic, the post-layout schematic, and all kinds of other things like that. Okay, so now we have our schematic editor. We have again the generic things that we use to design with, and then we have the process specific thing on the left that we design with. In our simulation environment, so once we have our schematic, we have to go into simulation. What we need for that is we need models of the transistors. We need a model that says how the MOSFET that's in here is going to actually work. Okay, so that's a model file. We'll learn quite a bit about that in a few lectures. Okay, and we'll have some statistical distribution that tells how these things vary across processes. So things aren't fabricated exactly like we expected, so there's some statistical distribution about that. Okay, that's what we're going to get from the foundry, and it's part of the PDK. On the other side, though, we have these different simulators. So there are going to be different levels of simulators. Our most accurate simulator that we're usually going to use is called SPICE, a SPICE simulator. There's a fast SPICE simulator, which is for doing bigger circuits. There's an analog mixed signal simulator, which allows us to mix between like a Verilog or some sort of other HDL, completely digital description, and some analog description, some transistor level description. And we're probably going to have a waveform viewer so we can look graphically at our results. And finally, we go over to the layout, and on the left side here, what we get from the foundry, we have to get a tech file that describes how our technology works and what it does. We have design and how we can actually make layers and lay them out and so forth. Design rules that tell us what we're allowed to do when we lay out our devices, and some sort of extraction tool rules that tell us how what the parasitics are of when we make such a type of layout. In our layout editor, we're going to draw our polygons, and then we're going to have tools from the CAD such as design rule check, layout versus schematic check, and an extraction tool. So let's dive into these things a bit more. The schematic editor is usually a graphical tool. We can also do it by hand, but we often use a graphical tool. So we can take such a simple circuit like this that has some sort of voltage source, a bunch of devices, which are resistors, maybe another voltage source. We give the nodes names. So these are all ground node. They're called 0, and this is net 1, 2, and 3. We have resistors between them. These are the sizes of the resistors and the magnitude of the batteries. Okay, it gives us an abstract representation for devices such as resistors or MOSFETs or whatever, sources like these voltage sources, wires such as these wires that are connecting them, and in general at this stage all of these wires are ideal. That means they don't have any resistivity, capacitance, or inductance. Okay, this is really easy to translate into a netlist. I guess it's not that easy. The tools are pretty complex, but we can look at this and straightforward translate it into a netlist, such as a SPICE netlist or a Spectre netlist. This is SPICE. These are two similar languages. Spectre is owned by Cadence, but SPICE is something developed by Berkeley, and it's in more of an open source language. In the SPICE language, when something starts with a V, it's a voltage source. Something starts with an R, it's a resistor. So this schematic here is translated directly into this type of a netlist. It says that V1, that's voltage source number 1, it's connected between nodes 1 and 0. The type of it is a DC voltage source, and it's a 24 volt voltage source. Say R2, that's this resistor, is connected between nodes 2 and 3, and its size is 8.1 kilo ohms. So that's a netlist. Then we have our simulation tools. So in the simulation tool, first of all, we're going to define our test bench, which isn't the thing we're actually going to lay out. It's just everything around it, such as the voltage sources and so forth. And we're going to also decide what results we want to measure. Okay, so there are different types of analyses or tests that we can run. We can run DC operating point, which actually solves just the basic Kirchhoff laws and Ohm's laws, and sees what our voltage and current is in each and every node and point in the circuit. We can do a DC sweep, which will solve DC operating points for different values of our sources. We can do a transient analysis, which starts at some condition and sees what happens over time, and an AC analysis, which puts some sort of operating points and starts sweeping the frequency around that. Okay, so what we're going to do also is we're going to define the outputs that we want to print or plot, and we're going to find variables that can enable us to do parametric sweeps around that. Okay, these things also are are translated into a netlist. So in SPICE, the test bench and the analysis and everything is in the same file or the same format as we define the schematic. So for example, here we have a DC sweep. We take the voltage voltage source that we saw here. It will sweep between 0 and 24 volts with steps of 1 volt. We can print the voltage, the DC operating point voltage at net 1, the voltage at net 1, and the voltage difference between nets 2 and 3. We can make a transient analysis that will run for 1 nanosecond and print values or have a time step every 0.05 nanoseconds. And we will in the transient analysis we'll print the voltage difference between nodes 1 and 2 at every time step. Okay, so we can also write scripts. Ocean scripting is the name of the script language that runs with Cadence Virtuoso, and we can use all kinds of other ways, like for example writing things in Python or C Shell or whatever to run these different SPICE simulations. Okay, there are different simulators, as I mentioned before. So SPICE or Spectre are the more accurate type of one. Fast SPICE, or what used to be called UltraSim, are a less accurate but faster type of a simulator to deal with big circuits. We have APS is a matrix-based simulator for SPICE to do accurate but very fast simulation. AMS XPS, it enables us to mix between digital designs like Verilog and some analog designs such as transistor level netlists. Okay, and we can use various models to describe devices. We can use corners where we take we'll discuss that, process corners and dissimulate them to show global process variations, and we can do Monte Carlo simulations, which actually roll the dice and see what, according to a statistical distribution, what the process variations are. We're going to discuss all that later on. Okay, layout. So after we got a good circuit topology, we can use the layout editor to produce a physical representation of the circuit. It uses a tech file to describe the various design layers and design rules. We do all kinds of things often to help this be faster. We use something called P cells or parameterized cells, where we can automatically generate a type of a layout representation of different devices, like a MOSFET with a certain width and certain length and so forth. We can use net names to connect between different areas of the schematic and the layout and kind of help us drive this thing, show flight lines where things are supposed to connect to each other, and even automatically route things. And we can use pin layers to describe schematic ports and pins to pass LVS. When you do this in different types of hands-on work, you'll learn how to do it. I will not discuss this in the lectures too much, but if you do labs that use these different tools, you'll understand what I'm talking about. Layout verification, that's DRC, LVS, and extraction. So DRC stands for design rule check. That ensures that the layout meets the design rule requirements. Layout versus schematic ensures that the layout truly represents the circuit. And parasitic extraction, it can also be called RCX or PEX, extracts the parasitic resistance, capacitance, and inductance of the layout. The common tools are Caliber by Mentor Graphics is one of the most common. Cadence has changed its name over time, but PVS, QRC, nowadays there's a new tool called Pegasus. Synopsys has a tool called Star XT. Okay, so DRC, DRC again is design rule check. That's something that we want to run and make sure that we meet all kinds of minimum widths and spacing and so forth. We can apply it iteratively, often in the layout editor. Cadence calls this DRD. Okay, they're complex geometric patterns. They're described in the rule file of the PDK. There are circuit level rules, there are chip level rules, and there are recommended rules, and we have to deal with them and solve all of them if we want to tape out our chip. LVS is the layout versus schematic tool. It basically is just a tool that takes two different net lists and compares them. The source net list is usually the schematic. So as I said, schematics pretty much straightforwardly compile into a net list. The target is usually the layout. The layout does not straightforwardly turn into a net list. So usually there's some sort of a tool that goes over and reads the different layers and makes whatever was laid out, turns it into a net list, and then it does this type of a formal verification where it tests that the source and target are equivalent. Okay, LVS is a tough thing. If you start at the wrong place, you're never going to get a good answer. So we need to give it like boundary conditions, and the boundary conditions in this case are the interface, the pins and the ports. We better make them correct, otherwise we'll have no chance of debugging it. So what I recommend is always to start with making sure your pins and ports are defined correctly, that they're compared, you have the same number of pins and ports, and they understand each other in the LVS debugging tool, and only after that try to understand why it didn't get the same number of devices or whatever that you expected. LVS also runs something called ERC, electric rules checks, which does things like checks bulk connections and shorts and so forth. RCX, or extraction, okay, that's a parasitic extraction tool. It creates a net list that includes the 9 ideologies of the layout, the actual device sizes, such as the diffusion length, which is something that we don't necessarily take into account with our schematic simulation. Okay, we look at resistance and capacitance of wires. We look at coupling capacitance between wires, and in order to run extraction, we must first run LVS. The output of the extraction is a list of net parasitics and a net list that can be plugged back into the circuit simulator. We call that post-layout simulation. Okay, extraction tools are Cadence has QRC, Mentor Graphics again uses Caliber, and Synopsys uses Star XT. So post-layout simulation is when we take these parasitics, we plug them back into the net list, and then we rerun our test benches to see if we get the same or better or worse results. Okay. Usually we use something like the hierarchy editor to just choose the different view that will be used by the test bench when it's running the simulation. So that's all for this lecture. We talked about a lot of concepts. You can see them all down here, and they're worth knowing all this terminology. A lot of complex concepts we discussed in this lecture. Okay, lots of three-letter words: PDK, HDL, EDA. Some four-letter words: ASIC, FPGA. Some two-letter words: IP, DRC, LVS, RCX, ADE. All kinds of things like that. Okay. Further reading, you can go to Digital Integrated Circuits by Rabbi. You can go to Elad Alon. Gave lectures about that in the past. It was called EE141. There's a lot of other stuff that I took it from, and several years of experience. So thank you, and next time we'll start talking about the manufacturing process.